Hello everyone, my name is Fernando and this presentation is about my final university project, which is a MIDI file hardware player, implemented in an FPGA platform. This project aims to be a solid base for future improvement in MIDI file compatibility. At the same time, this project intends to be a first approach to wavetable sound synthesis, which is commonly used in current digital piano. The development process of this project is mainly divided in the following parts. First of all, in order to understand the MIDI file format, it was needed to develop a console application, called MIDI parser, that can extract MIDI messages. Secondly, it was needed to familiarize with the Xilinx XOHW20 environment. After this, it was needed to elaborate a viable interpolation formula to apply wavetable sound synthesis. In order to achieve this goal, it has been developed another causal application, called Node Converter. The next step is the design of the MIDI hardware player. Finally, it has been developed an Android app, used as an external interface to comfortably use the hardware system via Bluetooth connection. The tools I have used in this project are the Linux command shell, Sublime Text 3, and the language C to develop the console application. To develop the hardware design, I used the Xilinx XOHW20 2018.2 environment and the language FHDL. Lastly, to develop the Android app, I used Android Studio and Java. Now, let's explain the sound synthesis mechanism that this project uses to generate sound. The wavetable sound synthesis mechanism consists in the generation of a wave sound with a defined frequency, applying interpolation between sound samples, which are stored in what is called a wavetable. This wavetable is formed by an ordered set of sound samples which globally represent a real wave sound that has been recorded. The wavetable used in this project corresponds with the sample data of the wave files. As an example, thanks to this mechanism, it's possible to generate the wave sound corresponding with the D node by using sample of the wave sound generated by the C node, without having the D node wave sound stored in memory. At the same time, the resulting generated sound maintains the natural sonority of the instrument that has been used in the recording of the wavetable. In this project, it has been used a linear interpolation formula between two sound samples to apply the wavetable sound synthesis. This formula is defined as follows. As we can see, this formula needs the frequency of the wave sound used as a wavetable, Fin variable, and the frequency of the wave sound that we want to generate, Fout variable. The I variable indicates the index of one particular sound sample that takes part in the wave sound we want to generate. The whole set of this generated sound sample will globally form the wave sound of the node that we want to synthesize. The following graphic gives a more intuitive view of this equation. This formula has been numerically proved. The next table shows some of these results. The approximate error we get per sample is around 0.02%. Now, let's take a quick view to the system. As this simplified schematic shows, the whole system is formed by 13 different components. In this presentation, I'm going to focus in the explanation of keyboard controller component. Keyboard controller receives a sequence of keyboard commands and consequently generate the sound by sending sound samples to the E2S interface component. Keyboard controller can only process one keyboard command at the same time. That's why the concurrently generated keyboard command must be sequenced by the CMD keyboard sequencer. We receive both the keyboard command generated from reading the MIDI file and the keyboard command generated by the user interaction with the external app. Depending on the keyboard command received, keyboard controller manages the activation and disactivation of the different node generation contained in it. These node generators apply the before-mentioned interpolation formula, which using the corresponding wavetable will depend on the node to be generated and is stored in the DDR2 SRAM memory. The resulting sound sample from each node generator are summed all together to get the final sound sample. Due to optimization reasons, all the operations with sample are done using fixed-point arithmetic. Finally, keyboard controller can also apply a reverb effect to create a deeper sound. After this brief architecture behavior description, let's check how this system works in real time. To summarize, the final result has been the successful realization of a digital piano that can play MIDI file and uses wavetables on sizes, designed as a complete hardware system. Furthermore, this design is also high parameterizable, allowing to easily configure both the maximum number of MIDI supported tracks and the polyphonic degree. For this presentation, it has been implemented a version with the following specifications. The FPGA board used in this project corresponds with the Digilent Nexus 4 DDR. At the same time, it has been used the Digilent P modules BT2 and I2S2. This implementation of the digital piano approximately uses a 22% from all the FPGA resources. The next table shows the amount of the different resources used by this implementation in the Nexus 4 DDR board. Thanks for watching.